Hi, my name is Tony, and this is a screencast about eMoflon, a tool for meta modeling and model transformation. What you can see right now is a small synchronization tool built using eMoflon, meaning we are starting from the perspective of an end user. The synchronization tool is able to propagate incremental updates between two textual languages used in the domain of manufacturing engineering. Above, you can see the current and previous versions of the first language, and below, the corresponding current and previous versions of the second language. Both languages describe the choice of a certain tool and the consequent movement of the tool's tip during the manufacturing process, albeit in a slightly different manner. Let's explore both languages by making some changes and seeing how they get propagated. The first change made here concerns the choice of the tool with the toolpath command. This has been changed in one language from FD14 to FD42, as you can see in the editor. The corresponding command in the other language is easy to spot, and one can also see that there is a simple one-to-one correspondence via the name of the tool. As you can see, the change was propagated successfully, and this can be repeated in the other direction by changing the value now from FD42 to FD44. This change is also reflected above and once again below. Another one-to-one correspondence can be demonstrated by changing the so-called feed rate of the tool in one language and propagating it to the other language. Once again, this works in both directions, and although the propagation seems simple, note that all other commands are comments, and the layout of both languages is perfectly preserved. A more interesting change concerns the coordinates of so-called goto commands. A goto command lists the values for x, y, and z coordinates, meaning that in this case, the z coordinate has just been changed from 28 to 27. Goto commands are more interesting as the language below is optimized for runtime efficiency and does not repeat coordinate values that remain the same from command to command. This means that the goto command above, listing all coordinate values, corresponds to the command below, which only sets the z coordinate, as this is all that changes in this case. Changing the value of the z coordinate is propagated correctly, therefore, by simply changing the value below, as z is again set to 25 in the immediate next command. If this value is changed as well, say to 20, then this corresponds to two changes below. First of all, setting z to 20, and on the next line, back to 25. Note that this wasn't necessary before. Let's see what happens if this value is changed from 25 to 23 below. This is interesting because the z coordinate is no longer set explicitly in the rest of the file, meaning that this single change has a much larger scope in the more verbose format above. This can also be demonstrated for the y coordinate, which is changed below and propagated above, and vice versa. Note in this case that changing the value above led to the creation of a new element below. Finally, a comment below is changed to show that this has no effect on the language above. And similarly, adding a new paint command above has no effect below, as paint commands happen to be relevant for the language below. Switching now to the perspective of the tool developer, we see that the synchronization tool was developed in Eclipse and that it's powered by standard Java code. In our case, the Java code is actually almost completely generated from a high-level rule-based specification, which we shall see in a moment. Before we do that, let's first of all take a look at the files created and maintained in the background. In essence, a triple of XML files is maintained for each textual format, and we can visualize one of these models or graphs just by dragging and dropping it in our eMoflon graph view. This is the parse tree from one of the formats, the top language to be exact. You can see the toolpath node here, and hopefully recognize some semblance to the code we saw earlier. This simple tree is transformed to a more connected and suitably typed graph, representing an abstraction of the language which is chosen to be just what we need for the synchronization. There are, for example, no paint commands or comments in this graph, and there are lots of useful additional cross-tree connections. The correspondence model can be used to explore the created traceability links between the model and the tree by simply dragging in connected elements and the correspondence links. We also have a dedicated view for correspondence links, which can be started with a simple click. We call this the integrator, and it displays both graphs as a vertical and horizontal tree, and the corresponding links as connecting points in the matrix. This matrix can be collapsed and unfolded as required. The integrator is not only a static view, but can also be used to step through the transformation by dragging in a so-called protocol of the transformation. This contains a list of the rules applied and the elements created. Once you drop in the protocol, the matrix unfolds completely and you can step through the transformation, seeing what element is currently active, displayed blue, which elements were created, displayed green, and which elements were translated in all previous steps, displayed gray. You can easily navigate both backwards and forwards in the transformation, and we also support breakpoints which are necessary to mark points of interest in large transformations. Switching back to Eclipse, let's take a look at the actual specification from which all this Java code was generated. eMoflon has both a textual and a visual syntax, and an editor for the latter is provided as a plugin for Enterprise Architect, a well-known UML tool. In this demo, I'll be showing only our visual syntax, but if you're interested in more details, just check out our handbook on our webpage, which handles both our textual and visual syntax equally. In the package browser in EA, you can now see a few packages containing the actual specification of our synchronization tool. Indeed, eMoflon is a tool for building tools, and a substantial part of eMoflon is actually built with itself. This is why you can see our eMoflon languages in the project as well. For the synchronization tool, we'll be using one of our internal languages, namely a simple tree meta model for interfacing with XML, standard parsers such as Antler, and structures in the file system. Our tree meta model is pretty basic. We have folders and files for representing parts of the file system, which is useful for some textual languages. The parse tree in our example, however, consists mainly of simple nodes with labels and children nodes. Our abstraction used for the synchronization consists basically of an ordered sequence of operations. For example, the toolpath we changed is a special kind of operation. Operations have arguments, and depending on the exact operation, there might be further, more specific references to arguments. To synchronize both trees resulting from the two textual formats, we use two bidirectional transformations that map the trees to our chosen common abstraction. To accomplish this, eMoflon provides a bidirectional model transformation language called triple graph grammars, or just TGGs. A TGG, being a grammar, consists of rules describing how two graph languages are to be built up simultaneously. One also describes how an explicit correspondence model, connecting related elements, is built as well, so it's not surprising that one needs a triple of meta models, which we call the TGG schema. As the meta models involved here are pretty simple, we just see that a CAM model corresponds to a single file, so no folder structures are used here, and that all other concepts are basically mapped to nodes in the tree. The actual TEG rules are organized in a so-called rule network, where rules can be composed and refined. For example, the toolpath rule refines a simple node to operation rule which is abstract, meaning that it only exists as a basis rule for almost all other rules in the network. One can take a look at the actual rule just by double-clicking it. For the simple node to operation rule, you can see that it requires 3 elements as context. This is why the elements are black, and that it creates an operation and a corresponding tree structure. These elements are green. TEG rules basically define a consistency relation where 2 models are considered consistent if they are the left and right components of a triple in the language generated by the TEG. Okay, if that didn't help, then just observe that you can read a TEG rule like this forwards, backwards, or as a rule controlling how updates should be propagated. For example, this rule states that if the operation is deleted, then this exact same tree structure must be deleted as well after dealing with all dependencies recursively. The toolpath rule refines the simple node to operation rule, meaning one doesn't have to repeat all nodes at links in the basis rule and can just add on new elements or refine existing nodes. The new operation node is, for example, now a toolpath. The operation node is now labeled toolpath, and the argument nodes are new and weren't in the basis rule at all. I personally like jumping back and forth between basis and refining rule. Some people like placing them side by side or above and below. Enterprise Architect even allows you to create links in diagrams, so you could add as many nodes as you wish from the basis rule without changing anything. It's all a matter of taste and training. To wrap up, let's take a peek at some of the other rule networks. This pretty network here handles, for example, arguments, which turn out to be quite interesting. In one language, you're namely free to omit argument values that don't change, but you don't have to. So the goal here is to preserve this degree of freedom as much as possible in the rules. This requires a non-trivial treatment of all possible combinations of argument values. Multiple refinement is also supported and turns out to be quite useful in practice. For example, after refining a chain of basis rules, like here, this rule refines 2 parents and not only combines them but actually changes them. So that means combining and refining as required. I'll leave you with this refinement network, hoping you've enjoyed the demo and that you get yourself a handbook from our website eMoflon.org and play a bit with TEGs.